Overview of section 1.1, where we learn about functions and function notation. This is the pre-calculus book from OpenStax. The idea with these videos is I'm going to try to talk through what I consider to be the most important topics in this section. I'm going to do so very informally. I'm not going to worry about hitting on every single thing. I'm just going to try to explain this how I would explain it to one of my friends if one of my friends was taking a class and didn't understand what they're learning in 1.1. So that'll be the goal of these videos. So the main topics in my eyes in this first section, well, the main topic, I guess, is functions. It's understanding what a function is. A function is a mathematical machine. You can represent it with a picture if you want. Here's my function right here. It's a machine, meaning I can put stuff into it, and the machine does something, and something else comes out of it. Inputs, outputs. That, in its most abstract sense, is what a function is a mathematical machine. I'll give you some examples. I'll tell you what is a function, what's not a function. But before I get too far into functions, I want to make the point that this is not one of those sections that you can just kind of skip over. Okay, I learned a little bit about functions. I guess I kind of get that it's this machine thing. Let's move on to something else that's less abstract that makes more sense to me. It's not. Functions is going to be the backbone of this entire book, frankly. If you're taking a pre-calculus class, what you're doing is learning about functions. You could argue that all pre-calculus is the study of functions. These are not going away. This is what you're going to study for the rest of this term or year or however the hell you're learning about functions. It's going to be a very important topic, and it's going to be kind of what calculus is devoted to. So this is not one of those cases where you should kind of skimp, you should cut some corners. I'll let you know when you can cut corners. This ain't one of them. So a function is this mathematical machine. Takes in inputs, gives out outputs. I like learning with examples, so I'll put an example right below this thing. Maybe you got the, I don't know, the square root machine. So the square root machine, what it takes in as inputs, maybe I put in the number 25 into the square root machine. And what this machine would kick out, what its output would be for this input would be 5, because the square root of 25 is 5. Similarly, I could put the number 9 into this square root machine, and what would come out would be the number 3. This is the square root machine. This is a more general function. Some vocabulary. The numbers that you can put into your function are what are called the domain. It's the domain of the function. The numbers that can possibly come out of your function is what's called the range of the function. We'll learn in the next section a lot more about domain and range, what numbers are in the domain, what numbers aren't in the domain, that kind of stuff. But for now, I just wanted to introduce them as vocabulary terms. When you see domain, think all possible inputs. What do you mean all possible inputs? Why could you, what kind of machine could you not put a number into? Well, think about this one right here. Think about if I try to put in -4, for example. The square root of -4, okay, kind of depending on when you learn that, you might have some clever response that has something to do with i's, but we're going to assume these are all real valued functions, meaning the things that can come out have to be real numbers. And so for our purposes, the square root of -4 is undefined. If you take -4 and try to put it up in this square root machine, you're going to break the machine because it doesn't know how to take the square root of -4. So -4 is not in the domain of this machine. Similarly, there is no number you can take the square root of and get, I don't know, -1. Can't do it. There's nothing that you can take the square root of and get -1. I don't care what you put in this machine, you will never get -1 out of it. So therefore, -1 would not be in the range of this machine. Again, the next section is devoted a lot more to domain and range, so I'll leave it there. I just want you to know that domain of the things you put in, range of the things that you can take out. So I guess I've kind of checked off domain and range. I don't know that I've given you a really good definition of what a function is. I've drawn you a little picture, and I've kind of talked about machines. But now that I know domain and range, I can tell you the number one, the important criteria, and this is very important, and I want to stress that it's important, apparently with some uppercase and some lowercase. There you go, important. The most important criteria for a function to satisfy is each element of the domain must have exactly one output. Exactly one, sure, output. All I'm saying is that this function has to be consistent. Not necessarily this function, anything. In order to be a function, the one criteria that it must satisfy, that your machine must do, is that if you put an 8 today, and maybe 7 comes out, And you put in 8 tomorrow, you better not have 9 come out. It better be consistent. For any given input, 8 in that example, there must be exactly 1 output. And you have to be a little bit careful. When I say inputs, I mean the elements of the domain, the things you're allowed to put in here. So you might argue that, wait a minute, -9, when you use that as the input, it doesn't have any outputs. Well, that's true. So that might seem to violate this criteria, but it doesn't because -9 is not in the domain. So I'm just talking about the numbers that don't break those machines. You can't put in one number and have 2 different numbers come out. Why? That'll end up being really important, and we'll get to why in a later video. I think for now, you're going to have to take my word for it that this is very important, which seems odd, and that is true. That are functions, they got to be consistent. For any input, there must be exactly 1 output. So what would not be a function? Well, the book, you can get at these really abstractly. That relations would be things that are kind of like functions that don't need to satisfy that criteria. So for a relation, I could put in 1 and have 3 come out, and then I could put in 1 and have 2 come out. What would that look like in terms of a function? Well, it would look pretty weird because it wouldn't be a function, so you wouldn't see it written as a function. But I guess you could argue that like if there was a plus or minus somewhere, that could cause 2 different outputs for a given input. Anyways, believe me, this is important. It's the number 1 most important thing you need to know about functions is that every element of the domain must have exactly 1 output. I'm going to call that my definition for a function. Although I don't know, that's really a definition, that's just kind of a warning there. Here's an example of a function. We talked about domain and range. What I now want to get to is another vocabulary word that has, actually I'm going to put this one on hold for a minute, and I'm going to jump down to evaluating and solving functions before I get to one-to-one. No, I'm not. I'm going to go in order. So one-to-one, I hit on this criteria. I made this such a big deal that any input must have exactly 1 output. So let's look at another function here. What about the, I don't know, the squared function? And so it's kind of like the square root function. In fact, these are very related in a sense that we'll make more clear when we get into the inverse function section. But for now, you don't have to worry about that. Squared function, all it does is you put numbers into it, like -3, for example, and the machine squares it. And it says -3 squared is +9, and 9 would come out. And I could put in a number like, I don't know, 3 maybe. And 3 squared is +9, so 9 comes out. And you're like, wait a minute, hold up, slow down. There's this big important note up here. You screwed something up right here because I have this same output right here, 9, for 2 different inputs. That's okay. That's not what this is saying. I did not just break the rule of a function. In fact, this thing in green right here is a function. Because what's going on here is I have 2 different inputs that have the same output, and that's totally fine. What makes something not a function is if you have 1 input that has 2 different outputs. So if I put a 9 in and a 3 came out, and then I put a 9 in and a -3 came out, this thing would not be a function. This is totally fine. It's just a little bit scary. It catches you off. Maybe it's not scary. Maybe that's stupid. It catches you. If I make such a big deal about this criteria, you might think that that's a little bit strange here. This is a perfectly fine function. But it is a little bit odd, right? It's a little bit strange that this machine is kicking out the exact same thing for 2 very different inputs. This function, and it is a function, it did not violate this important criteria. This function is not 1-to-1. This is the only time I'm ever going to write 1-to-1 like this. I'm typically going to be lazy and write it like this, 1-1. This function is not 1-to-1, this one in green right here. To be 1-to-1, it's a lot easier to say what's not 1-to-1. To not be 1-to-1, you must have 2. A function is not 1-to-1 if 2 different inputs yield the exact same output. So to be 1-to-1, it must not be the case. You can never have the same output from 2 different inputs. And I don't want anyone getting all technical, any lawyers in the room that are like, well, what if you get the same output from 3? Okay, that's bad too. 2 or more inputs. So this is not 1-to-1 because if you put in -3 and you put in +3, 9 comes out. That doesn't mean that every single output must have 2 inputs associated with it. That's has nothing to do with 1-to-1. To be 1-to-1, You can never have two different inputs take you to the same output. That's our definition of one-to-one. And I mention it now because I just made such a big deal about this criteria up here. It's related to this criteria, but it's important that you understand the difference between this criteria, which lets you know when a relation is a function, and this idea of being one-to-one. Okay, now I'll move on to what most of the questions you see in a section like this look like, evaluating and solving functions. So let's do an example down here. Example 1, I guess. I'm going to make some function, and I'm going to write it like this. Whoa, wait, hold on. What happened to the boxes and the flow charts and all that? Okay, I'm going to be honest with you. You're not going to see a whole lot of flow charts like this. The way you see functions represented, they can be represented in lots of different ways. Your book will show you ordered pairs, and it'll show you tables, and you'll even see diagrams like this. You're not going to see that once you get past this section. 9 times out of 10, the way you'll see a function represented is algebraically like this, which looks a little intimidating, but if you're really careful and you really understand what this statement here is saying, it'll give you a very deep understanding of functions, which will be important when you do some really challenging things later on with them. So what I want you to be able to do is take this right here and understand that it's really just a machine. The F right here represents the machine. By putting it in this notation, I'm implying that it is a function, therefore it passes this very important criteria. And what I'm saying is that if I put an x into my function, just the f right here represents the function, and then the parentheses, the x represents the input to the function, what the output would be 3x plus 1. So if you really want to write it right here, you could write a box and say it's the triple then add 1 machine. And so you put in a number like 2, and the machine triples it and then adds 1, so it kicks out 7, fine. You could write it like this, but it's more efficient to write it like this once you understand all this notation. So you're given this, you're given that f of x equals 3x plus 1. This is telling you there's some function, and when you put an x into this function, 3x plus 1 comes out. And I'm asking you 2 different questions. Question A, I guess, will be evaluate f of, I don't know, 7. Question B will be find all values of x so that f of x equals 7. These are very different questions. If you ignore all the English here and you just look at this versus this, they look pretty damn similar. They're very different, and understanding the difference will be key to understanding functions in this section. Evaluate f of 7. What this is telling you is that the input is 7. Remember, what's inside the parentheses here next to the f that represents the function is the input to the function. So what this question is asking you is, what comes out of the f machine when 7 goes in? Sorry for the penmanship. It's hard to read on a computer. Evaluate f of 7. Understand that this is what it is asking you, which it'll turn out is very different from what's being asked over here. Well, we can figure out f of 7. You could do it a couple different ways. You could do it like I was doing stuff up here where I just talked through stuff. He said this was the triple then add 1 machine. So if I triple 7, I get 21, because if you score 3 touchdowns and kick extra points and all, you got 21 points. And then you add 1 more, you got 22. Okay, I didn't need a football analogy there. 3 times 7 is 21, and 1 more is 22. If you put 7 into this machine, 22 comes out. You might just say 22 and that would be your answer, and that's totally fine. That's the correct answer. It's not a bad idea to get in the habit of writing it this way. Saying f of 7, well, this right here is kind of a blueprint for my machine. It's saying when you put some arbitrary number x in, 3x plus 1 comes out. So I could figure out what comes out when I put 7 in by changing all the x's over here in the output into 7s. I can make it 3 times 7 plus 1. And you're like, yeah, I got it. That's 22. I believe you. Okay, with this specific example, maybe you believe me that it's 22, but I bet I could come up with a machine that's complicated enough where you couldn't immediately determine the output for a given input, and it might help to have a way that always works. A way that will always work is by copying your blueprint here, but changing all the x's into 7s. And 3 times 7 is 21, plus 1 more is 22. So if you're asked to evaluate f of 7, your answer is 22, and the reasoning, the logic why is here. Note that really what you're doing here is you're simplifying. You're saying f of 7 is 3 times 7 plus 1, and then you're simplifying that expression as opposed to solving equations. Why do I make that distinguishment? Is that a word? Is because this next example will be very different. So this one right here is telling you that f of x equals 7. Note that the f of x is the output. The stuff on this side is 7. What you are being told here is that the output is 7. Over here, you're told the input 7, and you are asked to figure out the output. Over here, you're asked to figure out the input so that the output is equal to 7. Whereas over here, you're told that the input is equal to 7. So over here, the output's 7. Over here is the input 7. When I am testing this stuff, I don't know if all teachers are jerks like me, but I will ask you these two questions, one right after another, and in both cases, I'll have a 7 in here because I will try to confuse you. I mean, that sounds mean, but I'll try to give you a chance to show me that you understand the difference between these two questions. I could have said evaluate f of 3, and then I could say find all values of x so that f of x equals, I don't know, 10 maybe. Very different questions, and then maybe it's a little bit less confusing, but by putting the same digit in here, it might be a little bit confusing, but that's okay. It'll lead you to a deeper understanding if you understand how this question is different than this question, even though they look somewhat similar. What's being asked here is what inputs give an output of 7 in this machine. I guess there should be a question over here too. So how do you figure that out? Well, you could just look at it. You could be like, well, if there's a 7 over on this side of my machine, what must I put in? Kind of think backwards type stuff. And that's great. If you can think backwards, if you can look at this and be like, well, what would I have had to put in? Maybe a guess and check method. I don't know, maybe some way you can figure out what you could put into this machine and make a 7 come out. That's great. It's a good skill to have, but it's not how you should solve these. Because even if you can do that for this specific, somewhat simple function, I bet there's a more complicated function that you wouldn't be able to just look at and immediately tell that the output is 7. So here's a way you can solve these questions that will always work. You say, all right, I'm trying to figure out what values of x I can put into this machine to make 7 come out. Well, my output is 3x plus 1. And I'm told over here that the output is 7. So the output for this machine is 3x plus 1, but in this specific question, the output is 7. So all I have to do is say, when does this output equal 7? I have to solve this equation right here. And hopefully solving this equation is something that you've seen before. You solve it, you get x equals 2. Again, very different over here. Complete coincidence. This is 22 and this is 2. I guess nothing's a coincidence in math, but there's nothing that you're supposed to pick up from that, those digits being similar. Understand the difference in these two questions, that in this one, you are told the input and you are asking for the output. In this one, you are told the output and you are asking for the input. If you want to check your answer over here, you could do it. Right? You just figured out that when you put 2 into this machine, 7 comes out. Or at least that's what you think you figured out. You could check that by doing it similar to this. Note. Could check answer. By evaluating f of 2. Right? You could pretend there's a question C that looks a hell of a lot like question A, except instead of f of 7, you're asked to evaluate f of 2. Go ahead and do that. If you immediately know what your answer should be, pretend there's a part C down here. It says evaluate f of 2. If you can immediately see that your answer should be 7 based on your answer to part B, you're getting the hang of this idea with functions and understanding inputs and outputs. One final thing I want to talk about before I flip through the book is graphs. Graphs of a function. So I had mentioned earlier that there's different ways that you can represent a function. The most common way you'll see a function represented is like this, although you can also see ordered pairs and tables and other ways. I'm going to draw you a picture. And my picture is going to be a graph. And it's kind of hard to draw, but fine. Maybe I'll make it look like this. And note that I have a dot right here, meaning my function starts here. And then there's an arrow on this side, meaning it goes forever in this direction right here. This is a graph. This is a graph of a function. This is another way of representing a function. It represents the machine itself. It represents all the different inputs and the associated outputs for the machine. It's not immediately apparent what the rule of this machine is. We don't have something like this. We have a different way of representing it. And so every point that is on this line, and there's infinitely many points on this line, tells you one input-output pair. So, for example, let's see if I can find one. Here's one. It appears that this point right here is at 3, 0. Right? The x-coordinate equals 3 and the y-coordinate equals 0. When x equals 3, y equals 0. So what does that have to do with functions? Well, we use the letter x to represent the input for the function. So you might guess that when the input of the function is 3, the output is 0, and you'd be 100% right. What we're going to do when we graph functions is we always graph on the x-axis the input, and on the y-axis we graph the output. So if you have a point 3, 0, if on the x-axis 3 and on the y-axis 0, that means when you put 3 into this specific machine, 0 comes out. What about this one? What number would you put into a machine, into this specific machine? Maybe I'll call it G. I don't want to call it F because I used F down here. Typically when you're talking about functions, the letters F, G, and H are the most common. So I'll just use a different letter here so you don't get confused and think that's the same as this machine here. So I got this function right here, G, and when I put 3 into it, 0 comes out. If you can see how that represents this statement, that's fantastic. You're getting the hang of this stuff really well. Similarly, based on this point right here, I know that when I put -1 in, +1 comes out. So g of -1 equals +1 based on this point right here. And there's infinitely many more pairs that you can find. It looks like when 1/2 comes in, I don't know, something about 1/4 comes out, that's fine. You can get all that just from the graph of a function. Note the domain of this function is not from -infinity to infinity. We'll learn a lot more about that in the next section, but there's no output associated with -5, for example. So you might guess that -5 is not in the domain of this function. You'd be correct. We'll get more into domains in the next section. Just figured I'd mention that in passing. One last thing I want to do before I quit looking at this, because it's getting kind of ugly and hard to see, is go back and talk about this criteria and this idea of being one-to-one based on the graph of a function. Each element of the domain must have exactly one output. What would it look like for a graph to not be a function? Right? Because you could graph something that's not a function, that's fine. What would it look like? Here's an example. Fine. Something, I don't know, like this. Not a function. Why is this not a function? Because, I don't know, maybe this is 2 right here. When you put 2 into this machine, it looks like, I don't know, +2 comes out. Uh-oh, but wait a minute. When you put 2 into this machine, it looks like -2 comes out also. I have one input, namely 2, that has more than one output. Right, it's got an output up here and an output up here. So this thing right here is not a function. A quick way you can check to see if something is a function is this thing called the vertical line test. And the idea with the vertical line test, determine if a graph is a function. And the way you run it is to pass the vertical line test, any vertical line must intersect your graph at most one spot. To put differently, if any vertical, meaning straight up and down, line intersects the graph in more than one place, so for example, if I was running the vertical line test on this graph right here, maybe I'd draw this vertical line and be like, uh-oh, that's bad. It intersected in more than one place, 2 in this case. If any vertical line intersects your graph in more than one place, graph is not a function. And that's kind of stating the negation of the vertical line test. To pass the vertical line test, it must be true that every single line that you draw, every single vertical line, intersects your graph in at most one spot. It doesn't mean that just one line, it means every single line if you're going to pass the vertical. It's easier to fail than to pass. To fail the vertical line test, all there has to be is one vertical line that intersects your graph in more than one spot. That's it. The vertical line test is a way for you to figure out whether a graph is a function. So getting back at things we looked at earlier, like the definition of a function, We can talk about that in terms of a graph. We can also talk about the domain and a range of a function in terms of the graph, but that doesn't happen until our next section, so I'll save that for a little while. The last thing I want to talk about, and I feel like I've said the last thing like 5 times, is what's called one-to-one. It turns out you can also determine whether a function is one-to-one based on the graph of the function. So this graph that I drew right here, it is a function. It passes the vertical line test, right? Draw any vertical line you want, a line straight up and down, and it's going to intersect this graph in at most one spot. Passes the vertical line test. Is it one-to-one? Think about that for a minute. What does one-to-one mean? Well, let's see. We talked about that earlier. A function is, okay, here's when it's not one-to-one. Oh, this one was not one-to-one. To be one-to-one, you can never have the same output from 2 or more inputs. In terms of a graph, the output is the y value, the height, and the input is the x value, how far left and right you are. So if you're going to not be one-to-one, then what that's going to mean is there's going to be 2 different x coordinates that have the same y coordinate. We can come up with a test that's very similar to the vertical line test to determine whether or not a function is one-to-one. You are not one-to-one if you have the same output for 2 or more inputs. Does that happen here? I think it does happen here. Because look, for example, when I put 3 into this function, 0 comes out. But it looks like there's some point over here, I don't know, 0.8 or so, that makes 0 come out. So whether I put in 3 or 0.8, I get the same output. That's this case again. That's the not one-to-one case. Similarly, I don't know, it's hard to read, but it looks like when I put -1 in, +1 comes out. But when I put in, what is this, 3.7 or something, +1 comes out again. It's not necessarily bad. That's just bad if you're trying to be one-to-one. This graph is a function. And it's a function because it passes the vertical line test, but not one-to-one. And it's not one-to-one because I have the same height, the same output for 2 or more inputs. So how could you test that more generally? There's this thing called the horizontal line test. Very, very similar to the vertical line test. If any horizontal line intersects the graph in more than one spot, the graph is not one-to-one. Doesn't mean it's not a function, it's just not a one-to-one function. So for example, if I was going to draw, I don't know, this horizontal line right here, which is almost horizontal, it's hard to draw on a computer. That line intersects my graph in a bunch of spots, here and here and here, more than one spot, it's not one-to-one. You might argue that, but yeah, if you had drawn the horizontal line up here, you'd only intersect it once. That's fine. The horizontal line test is not saying that every line intersects in more than one spot to fail the horizontal line test. It's just if there is any line, you just need one, that intersects your graph in more than one spot, you've just failed the horizontal line test, and therefore your function is not one-to-one. Those are what I consider to be the main topics of this section. What I'm now going to do is kind of flip through the book and talk you through those topics. Okay, finally I'm going to flip through this book real quick and not talk about anything by any means. I'm going to spend like 2 minutes and just highlight a couple of key things. So our first section on functions here, you get this little introduction and you can read some examples if you feel like it. You can see what they consider to be the main topics here. We start out talking about actually it's not even a function at this point, talking about a relation. We're not even assuming it's a function because we haven't gotten to that one very important criteria that I keep hitting on. But they introduce words like input and output and fine, give you some examples. And then they draw you these pictures. These are their version of my machine pictures, I suppose. And what they're saying up here is this relation is a function because any of its inputs have exactly one output. Note that the inputs Q and R have the exact same output, N. That's okay. That doesn't mean it's not a function. That just means it's not one-to-one. But over here, this is not a function because one input has more than one output. So they get you through this definition of a function, which is a little bit more concrete and precise than mine. They give you some kind of abstract examples like the cost of donuts on a menu could be functions. Fine. Different ways you can represent functions. Here's representing functions with tables, and that's totally fine. You can do that. Different tables, and they get you these abstract ideas. But I kind of skipped over those because you're not going to see a whole lot of functions written that way. Skipping ahead a little bit, there's some more tables talking about functions. Here's where things start to look, I don't know, catch back up to what I was doing. They give you a function. This is their machine here. They're saying you put in a number, and what your machine does is it squares that number and then adds to that 3 times whatever your number was and then subtracts 4. So they want you to evaluate this function at these different points. Okay, first of all, I don't like this question. I think that makes sense for A, B, and C. Oh, I didn't know I could write on this. We could evaluate f of 2. Right? You can figure out f of 2 by just changing everywhere you see an x over here into a 2. F of 2 will be equal to 2 squared plus 3 times 2 minus 4, which is what? 4 plus 6 minus 4, which I think gives you 6. So the answer to part A here would just be 6. And you can do the same thing even if you don't have a number as your input. Your output would look a little bit weird. You could stick an A into this machine. Fine. What would come out? Well, everywhere I see an x over here, I'll change it into an A. How do you simplify that? You don't. You leave it just like this, and that would be the answer. So really all this question's getting at is, yeah, the more standard thing is to put in numbers, but you can also put in letters or even expressions. Everywhere you see an x, change it into an a plus h. Seems a little bit weird, but I guess it would just be a plus h squared plus 3 times this a plus h thing minus 4. So f of a plus h would be this guy here. I don't think it should say evaluate this at this point because that's not really what it's asking you to. It's just asking you to evaluate this thing. So this shouldn't be a D here. It should say, whole new question, evaluate this. Well, you can figure that out because you just figured out f of a plus h, or I guess I did, here. And you figured out f of a here. So you could take this thing and subtract this thing and divide by h. Your answer would just be a huge jumble of letters and this big mess of a fraction. Why would you actually, you could even simplify it so it's not a fraction. Rational expression if I'm being precise. So why would you bother doing all that? Well, this thing will turn out to be really important. This is what's called the difference quotient, and it will be an important expression when you get to calculus. So it's just being introduced here. Although I don't think this is a great question. It shouldn't say evaluate this function at this, because this is not the input, right? These are all inputs. This is just saying figure out what this whole thing's equal to. Being a little bit nitpicky, I'll move on. There's some solutions up there. We get into some graphs. I want to get to the bottom here. So they're saying you can even evaluate functions if they're given to you as a table instead of an expression. This is saying the inputs are 1, 2, 3, 4, and 5, and the associated outputs are 8, 6, 7, 6, and 8. So if you put 3 in, what will come out? Well, if you put 3 in, 7 comes out. That's what this first question is asking. The second one is asking you, what would you put in to make 6 come out? Well, it looks like 6 comes out when you put 2 in, but 6 also comes out when you put 4 in. So the answers here would be 2 and 4. And by the way, this is a perfectly good function, but it's not 1-to-1 because I got the same output here corresponding with 2 different inputs. Fine. You can do that same thing with the graph here. Right? Somebody could ask you the question, what is f of 3? Fine. If somebody asks you what is f of 3, or maybe evaluate f of 3, what you would say is, well, the input is 3. The x-coordinate is 3. And this is the only point on this graph that has an x-coordinate of 3. And the output, the y-coordinate associated with that input, would be 4. So if you're evaluating f of 3, you'd say that's equal to 4. Fine. And you can ask the question the other way also. Right? I could ask you, find all values of x so that f of x equals 1. Maybe I'll do that while I'm here. What this is telling you is that the output is 1. It's asking you the question, what were the inputs? Well, the output, the height, is 1 right here, and it's 1 right here. So it looks like the inputs that correspond with those outputs are 0 or 2. If you put 2 into this thing, 1 comes out. If you put 0 into this thing, 1 comes out. Do the same things we've been doing, but you can do them with graphs also. Determining whether a function is 1-to-1, we talked about that a little bit. This vertical line test, if you want it written more precisely, fine, here it is. Here's some examples. Not a function, doesn't pass the vertical line test. It is a function, it passes the vertical line test. Cool. Horizontal line test, pretty damn similar, except it doesn't tell you whether something's a function or not. It tells you whether something's 1-to-1 or not. This function is not 1-to-1 because, for example, this vertical line intersects your graph in more than one spot. Doesn't mean all vertical lines intersect your graph in more than one spot. It means there's at least one that does, therefore it's not one-to-one. Last thing, this is really why I want to come to the book to show you, is I made it sound like you can either represent a function with a graph or with an equation. That's not 100% true. Really, it's the same thing. It's the same machine. You can just represent it different ways, and often it'll be useful to have both representations. So maybe you'll be given a function in like f of x equals, let's get to one, x squared. And you want to know what the graph of that function looks like. Well, it turns out it looks like this right here. You can verify that. If you put 1 into this function, 1 is the input, you square 1, you get positive 1. Put negative 2 into the function. Negative 2 squared is positive 4. That's why this has a height of 4 here. The graph of f of x equals x squared looks like this. If you have a graphing calculator, you can figure that out. But I'm going to do a lot of things without a graphing calculator. So the idea here with these toolkit functions is there's 5 or 6 kind of basic functions, which it's a good idea to know what they look like, very generally speaking. So if you have a function like f of x equals 2, what this is telling you, it's a weird machine. You put whatever the hell you want into this machine, 2 is always going to come out. Note that the input, the value x, isn't even mentioned over here in the output. The output is completely independent of the input. It's a strange machine. You put whatever the hell you want into this machine, 2 comes out. What would that graph look like? It would look like this. Put negative 3 into the machine, 2 comes out. Put 0 into the machine, 2 comes out, and so on. That's all this is saying here. Here's another strange function, f of x equals x. Think about what that's saying. The x inside the parentheses is the input. So this is telling you when you take x and put it into the machine, x comes out of the machine. Wait, what? Whatever number you put into the machine is the exact same as what's going to come out of the machine. So if you put negative 3 into the machine, negative 3 better come out of the machine. Here's where negative 3 goes in. There's where negative 3 comes out. This point rep right here has a height of negative 3 because this x coordinate, the input of negative 3, corresponds with the output of negative 3 here. So it's a weird function, but it's worth looking at. Sure, it can have a name if you want, identity, whatever. Its graph would look like this. It would be this diagonal line here. Which makes sense, right? If you always want the x to be the exact same as the y, you'd end up on a diagonal line like this. Absolute value function, hopefully you've seen absolute values at some point prior. I won't define it here. Just an FYI, this is what his graph looks like. And you can talk yourself into that by looking at various x values and the corresponding y values. Quadratic function, okay. F of x equals x squared. Graph looks like this. I mean, I guess that's about all that it is just kind of believe that this graph looks like this for now. Cubic function, it looks very different from x squared. Note the differences in these two. The right side looks similar. Turns out the right sides aren't the same. This right side is steeper once you get past 1 than this right side over here. But they're similar, but the left side's totally different. This one goes negative, this one doesn't. This one has arrows on both sides, this one has dots. I have no idea why they did that. I'm going to throw arrows there because I think that would make more sense. Be consistent with the rest of the pictures. Reciprocal function, fine. Here's the last one we're looking at in our toolkit, 1 over x here. Turns out that that looks like this. I don't know if I'd say you should memorize all of these things, but at some point it's not a bad idea to know these, what are these, 5, 6? These 6 functions and kind of what they look like. I guess be able to talk yourself into this one. Same with this one, same with this one. This one you can either talk yourself into or kind of memorize. This one, I just memorize it. This one, I just memorize it. You can talk yourself into any of them, but I'm just trying to figure out what will be the least amount of work for you. And I think it's a good idea to just sort of memorize these shapes at this point in the class. Later on, we'll make these concepts a little bit more concrete. All right, I think I'm going to end that here. That's a little bit long, but hopefully that helps summarize section 1.1.